Hello, class. We're going to start chapter 8, that's rotational motion. And this is the last chapter of this course. And it's actually a very exciting lecture, but if we were meeting in person, we would have done lots of demos with this and worked on a lab that was really, really fun. But we'll just look into some of the examples theoretically, or maybe do some PHET simulation within the lecture. So let's get started with this chapter. So basically, from this chapter, we are only going to cover 8.1 and 8.2 sections. There are just two sections that we are covering now. It's a very difficult concept to understand torque and other higher concepts of rotational motion without doing labs. Physically, and also without looking at demo that we have so many demos for this particular chapter in the lab. So that's why I'm restricting this chapter instruction to only two sections. So it's equally fun and very easy to learn. So we'll talk about angular quantities and constant angular acceleration, something which we did for the linear quantities like linear velocity, linear acceleration, and we also did constant acceleration in chapter 2 and 3. So we will look at this chapter now. The quantities that we use here are all about angular or rotational motion. So where do you see rotational motion in your daily life? Probably because when you drive your car, that's where you see your rotational motion first. Merry-go-rounds in the parks, the windmills, the fans, the microwave in the morning that you use, where the rotating table rotates, that's rotational motion. Even opening the door is a rotational motion because it's on its hinge, and once you push it, it traces a curve, so that's also a rotational motion. So many other countless examples for that. And other than that, there is rotational motion of which you are a part, more subtle, involving you as well. So if sun is somewhere over here, that means you are within that solar system somewhere as a tiny speck of dust. So at the center, we think that there is a black hole, and this entire material is always rotating around the center, which has a high gravitational pull, and because of that, the material rotates faster and faster closer to it, and as we go away and away from it, the speed reduces. So that's one more example of rotational motion. Another example of rotational motion can be a figure skater rotating. So why do tornadoes spin? Tornadoes are also one of the examples. But have you ever wondered, why do they spin? And why do tornadoes spin rapidly? So basically the answer is that the air masses that produce tornadoes are themselves rotating. And when the radii of all of the air masses decrease, so when the radius decreases, their rate of rotation increases. So that's the same thing that happens to the figure skater when her arms are wide. If this is a figure skater, I know this is not the best diagram. So when her arms are wide open, she's slower compared to when the arms are when she brings the arms closer, she spins faster and faster. So the same way, the tornadoes also spin faster when the radius starts decreasing. So an ice skater increases her spin in an exactly analogous manner, just like you saw for the tornado. The skater starts her rotation with outstretched limbs and increases her spin by pulling them in towards her body. So the same physics describes the spin of skater and wrenching force of a tornado. That's basically we call the phenomena is called angular momentum conservation. You learnt linear momentum in chapter 7, but there's something called angular momentum also that is conserved. Momentum, whether it is rotational momentum or angular momentum, whether it is linear momentum, is always conserved. So clearly force, energy and power are associated with rotational motion. These and other aspects of rotational motion are covered in this chapter, so we'll see what we are going to discuss here. So we'll begin with our first section, that is angular quantities. What are the quantities that are going to help us define some other quantities like angular speed, angular acceleration? So we begin with the rotational motion. So in a purely rotational motion, all points of the object move in circle. So if there's a point here, if there's a point here, and if I'm at a disk position, if there's a point here, this is a disk. So everything rotates with respect to the center. That is the axis of rotation. The radius of the circle is given as r. All points on the straight line drawn through the axis move through the same angle in the same time. That means if a particle is here and after some time it is over here, or if the particle is here and then after some time it is here, or if the particle is here and after some time it is over here, the angle for all of these is going to be same. There's a relationship between the theta. So theta represents the angle between the initial position and the final position, and L represents the length of the arch, and r is the radius. So this is a famous relationship between theta and theta L, the length of the arch, length of the arch, and radius of the circle. So we'll remember this, and there is a score of other ways that you can write this. If you're going to find the length of the arch, you can write this as L is equal to r into theta. And if you're going to find r, the radius of the circle, you can use it as theta over, sorry, not theta over, that's L over theta. So you can use this equation in numerous ways. So this basically we discussed in uniform circular motion also, and when we were talking about objects going in circle. So this was briefly touched in chapter 5, I guess. So then, so let us move to the next part. It's a good idea at this time to understand what conversion of units means for an angle from a degree to a radian. So we can express the angles in radians. So you have a calculator, and sometimes I asked you, oh, change the mode of your calculator from degrees to radians. So when you're calculating these, you may have to do these for these problems. So basically, let us consider an example. Before we go into this, let us consider an example, a bike wheel. So a very, very common example. So a bike wheel rotates 4.50 revolutions. How many radians has it rotated? So 4.50 revolutions. And we know one revolution means a complete circle, that is 2 pi radians, right? So one rev is 2 pi radians, or you can say 2 pi rad. That is also one rev is equivalent to 360 degrees, which is 2 pi radians. So we can basically convert from degrees to radians. That is what we are doing in this problem. Here, let's remember that theta is equivalent to L over R, or L is equivalent to R into theta. So this is a very important relationship between the length of the arc and the radius and theta. You will appreciate it in a little while when we are going to compare other equations as well. So here L represents the complete circle. If I complete the entire circle, the L can be 2 pi r, right? And 2 pi r is the complete perimeter. If the length of the arc is the entire circle, so that length of the arc 2 pi r, and your angle will be given by theta is equivalent to, theta is L by R. So I know theta is equivalent to L over R. So R into L by R. So that is what it means. L is equivalent to 2 pi R. So basically 360 degrees, the angle, is equivalent to 2 pi radians. That's how it's done in your calculator. Within the calculator, they all they do the conversion. Okay, so which means 1 rev is equivalent to 2 pi radians is equivalent to 360 degrees. So basically, how much is the conversion for a radian to a degree? So if I say 360 degrees is equivalent to 2 pi radians, therefore what is 1 radian equivalent to? How many degrees is 1 radian equivalent to? So we'll do this way. 2 pi radians is equivalent to 360 degrees. 1 radian, divide both sides by 2 pi, 360 divided by 2 pi, and 2 pi is 6.28. You can solve that with the calculator. You get 57.3 degrees. So that is why in your calculator, if you are in the radian mode, it is measuring different compared to the degree mode. So that is why sometimes your answers come out wrong, because 1 radian is 57.3 degrees. Now let us solve these problems and see how we go about them. Now we have to express the angle in radians. So for example, we have been given part A 45.0 degrees. So you can pause this video if you are watching and try and solve them yourselves, and while I'm working on them as well, you can stop the video, start working on the problems yourself as if you were going to be doing them in classroom. So to convert from degrees to radians, so we'll say 2 pi we write this briefly as 2 pi rad is equal to 360 degrees. So the degree and degree will get cancelled. So basically when you divide 45 by 360, you will get pi by 4 radians, or that is equal to 0.785 radians. Do the same with part B. So I'll basically not solve all of them. 60.0 degrees. If I have to convert into radians, 2 pi radians over 360 degrees. Do the same math here. The degrees are gone. We'll have the final answer as pi by 3 radians. Then you want to solve it properly, and you get 1.05 radians. So basically 60 degree is 1.05 radians. In the same way, we can solve C, we can solve D, we can also solve E. So you go ahead and solve them. I'll just simply give you the answer. 90 degrees is pi by 2 radians. 90 degree means pi by 2 radians, which we generally know. But what does it stand for? It's 180 by 2. So it will be 1.57, it's 3.14 by 2. That is 1.57 radians. And similarly, what about your D, part D, which is 360 degrees, will be 2 pi radians because it's simple. 360 degrees will be is equivalent to 2 pi radians because we already use this. That is nothing but 6.283 radians is the maximum of all. And similarly for 445 degrees, how many radians is it? So sometimes you keep on rotating, and the number of turns you take also constitutes the angle that you have traversed. So although we have 360 degrees, the maximum angle, but 445 degrees means it went for next turn. So 245 degrees into 2 pi radians, I'm just showing this one because it's greater than 360, 2 pi radians over 360 degrees for one. That means you can already see that it is 89 pi over 36 radians, which when you solve will be 6.283 radians. Actually no, not 6.283 radians, it's bigger, it's 7.77 radians. Okay, so this is how you will work on these kinds of problems. So now this we were able to describe with the help of theta is equivalent to L over R, converting your degrees to radians. Okay, next we'll talk about the most important quantities that are called angular quantities. So this resembles, if you look at this can be a replica of simple displacement or a linear displacement. The stuff that we learned in chapter 2, where delta x is x2 minus x1. Same way, if an object or a particle is traveling, a body is traveling from one point to another point, and the angle is theta 1, and then it moves to another position and the angle changes. So the displacement is, the angular displacement is the displacement or the change in the angle, and is given by delta theta, which means theta 2 minus theta 1. Now that I know the displacement, so if I have to find out average angular velocity, remember the word angular. We are using the word angular because we are in rotational motion. Okay, so that's why we are using the word angular here. And in chapter 2, you used simply displacement, velocity, instantaneous velocity, acceleration, which was actually linear. So chapter 2 was based on linear quantities going in one direction. But these quantities will be redefined, but with new symbols and new definitions for rotational motion. So once we have defined the angular displacement, we can now define our angular velocity. The average angular velocity is given by change in angular distance. That means displacement over time. See, here also we are defining velocity as displacement by time, but the only switch is we are using angular. The word angular is incorporated because we are measuring change in angle. So the unit for this is radians per second, which translates to meter per second directly. And we can rewrite this later. I'll show you later what else we can do with this omega. So then we have instantaneous angular velocity. That means velocity at a particular instant. Remember, we discussed similar quantity called instantaneous velocity. Instantaneous velocity in chapter 2, which means the velocity at that very minute. And similarly, we have instantaneous angular velocity, which means when the time lapse is very, very, very small, and the shift in angle delta theta over delta t for that brief interval of time at that very instant gives the angular velocity. Okay. So next we'll discuss other quantities that are related to angular velocity. So if you remember linear motion, acceleration, average acceleration is final velocity minus initial velocity over change in time. We can define angular acceleration. Now you must be wondering, what is this omega? This is not a W. Sorry for that. I did not express this. This is an omega, which is denoted as small case W-like structure, but it is not W. It's curved inwards and it is called omega. It's a Greek letter used for angular velocity, and that is basically, you cannot use V for this because V is linear velocity and omega is the rotational angular velocity. So that is why we have a different symbol for this. Similarly, if A is the linear acceleration, I cannot use A for the angular acceleration. So we have a new term alpha, which is also a Greek letter and is called angular acceleration. So alpha in Greek, angular acceleration. So the basic definition of the acceleration is not changing. We are still using change in velocity over time, but this time we are not using your linear velocity. We are using final angular velocity minus initial angular velocity divided by time. Therefore, I get change in velocity over time as angular acceleration, right? And similarly, I can define the quantity instantaneous acceleration, that is acceleration at that very minute. That means where the time limit is very, very small. So delta omega, we call this as omega, and represents velocity. Which type of velocity? Angular velocity. And change in angular velocity over time will again give me the instantaneous acceleration in rotational motion called the angular instantaneous acceleration. So just remember them, these are definitions. Just like we had started in chapter 2, defining speed, defining velocity, then we went ahead, gave their mathematical properties, gave the formulas for these, and defining acceleration, defining instantaneous acceleration and average acceleration. So same we are trying to do here in rotational motion. So then we'll now show how linear quantities are interrelated to angular quantities or we can say related to rotational motion quantities, or related to rotational motion. So there's a little explanation that can go in here. Angular velocity is not constant when a skater pulls in her arms. So the velocity is changing, and if the velocity is not changing, then we won't have acceleration. So the figure skater, when she pulls the arms inwards, her velocity is changing. Her angular velocity has changed. So when a child starts up a merry-go-round from rest, or when a computer hard disk slows to half when switched off, in all these cases, there is angular acceleration because angular velocity has changed. So if angular velocity is not changing, we will not have any acceleration. You must understand acceleration means change in velocity per unit time. So let's see how these quantities are related to each other. So we have v as the linear velocity. So if an object is moving in a circle, so for example like this, if this is a disk, if this is your compact rotating disk in the computer, nowadays we don't use them, but think about the floppy disks, or think about the these disks that you use if you still have them and use to watch movies on. So if there's a speck of dust here and it's rotating, so you know that there's a linear velocity that works tangential to this track, and then there is a radius from the center, that's the distance from the center, and then if the speck of dust was over here, the r would be different, and if the speck of dust was at the rim, then the distance would be the actual radius of the disk. But if the particle or the speck of dust was closer to the center, then we have to find out how the motion is affected by as the distance increases from the center. So you will understand that once you get to understand this formula. So we know that linear velocity is given by length over time, that is change in length or change in distance. For this case, our change in distance is the change in length of the arc. So if initially we moved from here to here, then after some time it's over here. So there's a change in the length of the arc that we have actually obtained in a change in time, in a certain change in time delta t. So behind I determined a relationship between theta, L and R. So that time I was telling you, watch out, we'll need this at that to define other quantities. So L is equivalent to R into theta. So instead of writing V is equivalent to delta L over theta, I'll write delta over delta t, but instead of L, I will write R into theta. Okay. So R stays same for that particular radius. If I'm talking about the rim, the R doesn't change, but the velocity changes because it's moving. So there should be change in the acceleration also, or there is an acceleration because the velocity is changing. So R is constant, I'll take it out. Therefore, I get delta theta over delta t inside. Okay, but what is this delta theta over delta t? It is angular displacement over time. That is why this quantity is omega. That is why we are writing it as omega, because behind we describe this as omega as angular displacement over time. So this is a significant equation where we are relating linear velocity. So linear velocity is always tangential to the circle, and omega is always going in in the same direction as the rotation of this disk, right? So basically, V represents linear velocity and omega represents angular velocity, and there's a relationship between the two through the radius or through the position where it is. So for this particular case, our point P is over here. So if this is a track on a disc, on a music disc, so this R represents that point, then there is another track. So maybe I'll name it as R1. So I could say V, if I have to find the linear velocity at this point, I'll say, okay, V is R1 into omega. So you must understand, if I go farther and farther away from the center, the linear velocity will increase. Okay, remember, V is equivalent to R into omega. So if R increases, V will increase. So that means there will be maximum value of linear velocity at the rim of the disk. So it will be fastest, going faster toward at the edge or at the rim of the disk. So that is the linear. But what about omega? So if I have to find out what is can I rewrite omega in this form? So omega can also be found out from this equation if I divide both sides by R. So that will be V over R. This is an interesting relationship. The linear velocity increases as we go away from the center, but the angular velocity decreases as we go away from the center, because there is a inverse relationship. So if R increases, omega will decrease. That means the angular velocity is slowest at the rim and fastest at the center. So please remember this relationship from these two equations. So this should be clear because V is directly related to R here. R increases, linear velocity increases. For this equation, R increases, angular velocity decreases. So we'll do more problems on these in order to understand this. Next, we define another quantity called angular acceleration. What is the relationship between linear acceleration, or also called tangential acceleration, and denoted by A tan? Just like behind, you found out a relationship between linear velocity, radius, and the angular velocity. In the same way, we will find relationship between tangential velocity or the tangential acceleration or the linear acceleration, and the angular acceleration alpha that we discussed. So we begin this way. If you understand this equation over here, so let me do it for you. We know that linear acceleration, which we say it's tangential. Tangential means it's linear because it's not rotational. In previous chapters, you have been writing simply as A, but now that we are talking about rotational motion, we write it as tangential. So if P is a particle here, and if we are going right this way, tangential acceleration is always outwards, while as the radial acceleration due to the centripetal acceleration is always towards the center. And there is also angular acceleration, which is given by alpha. So the linear acceleration is given by delta V over delta T. Just now we learned that V is related to there's a relationship between V and R and omega. V is R into omega. Okay, so instead of writing V, so I will write R omega. So that will be equivalent to delta times R omega divided by delta T. Now again, we'll do the same thing. R is constant, so R does not change. So A tangential, which is also the linear, R comes out, we get delta omega over delta T. Okay, and this delta omega over delta T is nothing but angular acceleration, because delta omega represents change in angular velocity over time. So change in velocity over time simply means acceleration, but since this is change in angular velocity, we call this as angular acceleration. So hence there is a relationship between linear acceleration and angular acceleration through R. Again, now watch this. The linear acceleration A tangential is equivalent to R into alpha. If you were listening to me carefully behind, where will the tangential acceleration be greater? Towards the center or towards the rim? All right, by now you must have seen there's a direct relationship between tangential acceleration and the radius. As the radius increases, so will the tangential acceleration. So the maximum acceleration in the tangential or the linear form will be maximum at the rim compared to the center. But vice versa is true. If I divide both sides by R, I'll get alpha is equivalent to A tangent over R. These are all conceptual. So that means angular acceleration, just like angular velocity, must be fastest in the center as it is going and slowest towards the edges. So alpha is slower towards the rim. So all angular quantities are, when they are closer to the center, have greater magnitude compared to the linear ones, which are maximum towards the end. So you can remember this way. We are not done with accelerations yet. We need to define now third type of acceleration, which is the centripetal acceleration. All of us know that when an object is going in a uniform circular motion, we have AR, the center seeking acceleration, which is given by V square over R. Now, since we are talking about V is R into omega. So that is what we have done here. We have substituted for omega V over here as R omega. So when you work on this, this comes out to be R square omega square over R is equivalent to AR. So one of the R is going away. You get R omega square, or you can also write it as omega square R. So there are three different types of representations you saw for acceleration. A tangential, which is the linear velocity, R into alpha. Alpha, the angular acceleration, as A tangential over R. And also you saw the radial acceleration, which is the centripetal acceleration, given by omega square R. So keep that in mind, and we will solve some problems now. So the textbook, this is a textbook problem, number 4. So take a look at this problem. You can pause my video and think about the quantities that are given and what the problem is talking about. So we have a blender that you use in the morning to make smoothie, and the whatever here is swirling. There's a motor. The blades in the blender rotate at 6,500 revs per minute. RPM means revs per minute. Okay, so when the motor is turned off during the operation, the blades slow to rest in 4.0 seconds. What is the angular acceleration as the blades slow down? So we have been asked to find out alpha. So if I have to find out alpha, I need to know what is the delta. Alpha is equal to delta omega over delta t, right? So that means I need to know my final angular velocity and the initial angular velocity. See, I'm maintaining the same notation, omega with no subscript as final and omega naught as initial, divided by delta t. So has he given me any quantities? He's given me the blender rotates, when you turn it on, the blender rotates at the rate of 6,500 revs per minute. Looks like some revs per minute, like distance over time kind of a scenario. So that tells me this is rotational speed or angular velocity. Angular speed is given. So we have to find that out. So omega naught is given in a strange form. It's given as 6,500 revs per minute, which can be also read as RPM. So my job is to convert it into radians per second. Radians per second is the official SI unit for angular velocity, and radians per second squared is the official SI unit for angular acceleration. I forgot to mention it there, but so now I have to convert it to radians per second. So that means the revs need to be converted to radians, minutes need to be converted to seconds. So to get revs, we know I need to cancel this rev. To get radians, I have to somehow see that revs get cancelled. So rev got cancelled by putting 2 pi radians equivalent to 1 rev, and I want the seconds. So we know that we can write 1 minute. 1 minute is 60 seconds. I think everything has been taken care of. All my units are in good order, and I can write this as 6,500 multiplied by 2 pi radians divided by 60 seconds. So why don't you take a calculator at this point and start getting the values here. Remember to switch your calculator to radian mode. 6,000, actually it's not needed, so you'll anyways get the answer. 6,500 multiplied by 2 pi should give you 681 radians per second. Now that we have omega, we have the initial omega, and we also have the change in time as 4.0 seconds. He's saying the blender is finally going to stop and it's going to slow down, so it is 0 radians per second. Therefore, angular acceleration alpha, which is omega minus omega naught over delta t, you'll get a negative value, same like we get for deceleration or negative acceleration, 0 minus 681 radians per second divided by 4.0 seconds. So your alpha, the angular acceleration, is minus 170 radians per second square. Now this is not going to be meters per second square. We are talking about radians per second square. We are not talking about regular linear acceleration. We are talking about angular acceleration. That is why we represent it in radians per second square. So it's the SI unit for acceleration, and radians per second is the SI unit for angular velocity, and radians per second square is the SI unit for angular acceleration. So that solves this problem. Now let's move on to another problem. So we have a child rolls a ball on a level floor to another child. If the ball makes 12 revolutions, what is its diameter? Kind of a little tricky. This is more of a conceptual problem. So how will you be able to find the diameter from knowing that a child is rolling a ball on a level floor, which is 3.5 meters, to another child? So basically, there are two kids here, and this person, this is 3.5 meters. And he's rolling the ball. So eventually it's going to reach here. If the ball makes 12 revolutions, what is its diameter? So it's rolling, 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 rolling. So the ball makes 2 pi r. So 2 pi r is the perimeter, which also means pi into d, because 2 pi r means pi times 2r. That is nothing but pi into d. Twice the radius is the diameter. So the ball rolls pi d of linear distance. So every time it's going pi d times pi d times pi d. So this happens 12 times. So 12 times it's going and reaching the other end. So this ball basically can be used as a measuring tool. So 12 times it's going on that 12.0 revs, and this ball pi d in meters basically divided by 1 rev. Okay, so this is 2 pi r, or 2 pi r is equivalent to 1 rev. That's what it means. This is nothing but we are using the conversion. 12.0 revs, if I have to convert them into the diameter pi d, so the rev and rev goes away. We are left with basically 12.0 into pi into d over 1 rev. That should be equivalent to, that is equivalent to 3.5 meters. So that's what is given already. There's some problem with the pen, I'm sorry, but there's nobody out there in college to help me fix this. So 3.5 meters. So you roll this ball, which has a diameter of d, 12 times over this length, 3.5. So basically 12 times this is equivalent to 3.5 meters. Simple. So now this can help me get the diameter of the ball. So if you look at it, divide both sides by 12 pi. So I get d is equivalent to 3.5 meters divided by 12.0 into pi, which becomes equivalent to 9.3. You can take your calculators at this point and start solving. So this is basically a very small diameter for that ball. If you 9.3 meters divided by 10, it's divided by 100 meters. So that that tells you that in centimeters how much is this. Okay, so this is how we can use these basic conceptual understanding to solve these problems. Let's go over one more problem, then we'll probably call it a day. A grinding wheel, which is 0.35 meters in diameter, rotates at 2200 revs per minute. So a grinding wheel. These days we don't have it, but in olden days you used to have grinding wheel. You can compare it to the blender. Okay, so the diameter of the wheel is 0.35 meters and rotates at 220 revs per minute. So whenever you revs per minute, it's the angular velocity that is given. So be careful to understand this problem. It's not that easy, but has little things conceptually to be understood. Calculate its angular velocity in radians per second. So we have been given omega as 2200 revs per minute, and my job is to convert it to radians per second. 2 pi radians 1 rev, and instead of a minute, 1 minute over 60 seconds. So the minute in minute goes away, the revs and rev go away. My omega in radians per second, if you look at it, 2200 multiplied by 2 pi multiplied by 2 pi radians and divided by 60 seconds is equivalent to 230.4 radians per second. If you are solving further, you should use this value, but otherwise the answer in 2 sig figs will be 23.230 radians per second as 2 sig figs. Okay, so that was part A of this problem, and part B asks us to find out, calculate its angular velocity in radians per second. What are the linear speed and acceleration of a point on the edge of the grinding wheel? So basically he's asking you to find out v, the linear speed, which is v is equal to omega into r, and he's also asking you to find out a tangent A radial. So at the A radial is omega square r, so you can use this these equations to find out. We know r is given as 0.35 meters in diameter, but in order to find r, you have to divide this by 2. So r is equal to 0.35 divided by 2, since this was diameter. So go ahead and substitute the values of omega. Omega is the radial velocity or angular velocity, and 230.4, I will use the entire one, multiplied by r as 0.35 divided by 2, because we are using the radius. And so we will get the velocity as, because this is v, it will not be radians per second, it will be meters per second. The units for the linear velocity is meters per second. The units for this is radians per second, and r is anyways in meters. So 230.4 multiplied by this gives 4.0 into 10 to the power of 1 meters per second. This is the scientific notation for this one. Same way, we can go ahead and find AR. which is omega square r. You already know omega. That is given as 230.4 whole square multiplied by r, 0.35 over 2. When you work on this in 2 sig figs, you should get 9300 meters per second square. Can you believe it? These numbers are really high. Meters per second square. Okay, this is how you solve these problems. I'm looking at any other problem. No. So we'll look at other quantities next time. Basically, you learned the SI unit of angular velocity is radians per second, and the SI unit of angular acceleration is radians per second square. And the linear ones have their own units, as you know already, meters per second, and acceleration AR or A tan will be meters per second square. So let's take a look what we are working on over here. Objects farther from the axis of rotation will move faster. This is the same thing that we discussed. All the objects that are farther and farther away from the center will be governed by this equation r omega. So if r increases, your linear velocity also increases. That is what it means for this one. Your v of linear will increase. The frequency also, we can define frequency. Frequency means the number of revolutions per unit time, which is per second, and frequencies are measured in hertz. Frequency is reciprocal of time. So if frequency is also represented as 2 pi of f is equivalent to omega, and that 2 pi f is equivalent to omega represents angular frequency, and we can also relate to this as f is equivalent to omega over 2 pi. So I don't think we will need the use of this equation in this chapter, but yes, time period is reciprocal of frequency. We use this all the time. So I'll stop here. I think this is a good spot to stop, or actually after this slide, because this completes the 8.1 section, showing you various formulas that you have used. This is showing the corresponding relationship between linear and rotational quantities. The linear quantity x is, or probably delta x, is displacement, which we call as x minus x naught, and its equivalent rotational counterpart is delta theta, which is change angular displacement. That means theta final minus theta initial, theta minus theta naught, and over here x minus x naught, and the velocity linear, while as the angular is omega, and linear or tangential acceleration and the rotational acceleration. Then how are they combined together? How is linear combined to the rotational? This is something that you should always remember, that linear displacement is related to angular displacement through r. It's the same thing as L is equivalent to r theta. The arch, where instead of x we could also write L, because that's the linear displacement in the circle, and v is equal to r into omega. So we saw this behind, and a is equal to alpha through r. So we'll work on more problems on this, and I will stop here for today and see you with the part 2 next time. Part 2 of this next time, and do give it a good reading from your book, chapter 8, This is just the first section, and work on some of the examples that are given there as well. Okay.